my slides now, yeah?
Yes.
So I'm going to talk about sort of the second path that Hannah had on her slides. That is, we're trying to solve now materials from first principles. So as you've seen, these materials are made out of atoms. And what properties they have really depends on how the different chemical elements are arranged. And as you know, it's a sort of the atomic number, the nuclei that you have that determine which elements you have. But what really leads to most of the behavior you see is actually the electrons that sort of form the glue that holds the atoms together, that form chemical bonds, that are responsible for the electric, the magnetic, the optical properties. So as you see, there are sort of a number of examples where really the electron behavior is very important for the behavior. So on the bottom left, you see a magnet. Magnetism is actually quantum, comes from quantum mechanic behavior of the electrons. And another example in the middle, that is a piece of gold. We want to understand what, for example, is the color? What are the optical properties of a material from first principles? Here on the right, you have that's actually antimony. So you have an element that is at the border of being a metal and a semiconductor. So we want to understand how is the electric behavior of a material affected. And here at the top, this is actually from an experimental measurement, how different atoms are distributed in a nanoparticle of iron and platinum. So you see the iron and the platinum atoms distributed. And now if you know where these atoms are, can we calculate what is the magnetism, what is the electric conductivity of such a material? And as Hannah showed you, the equation that is responsible for this is the Schrödinger equation, but it is not sufficient to solve the Schrödinger equation just for one electron. You actually have many electrons. So you can see this sort of as an eigenvalue equation. And as you see, we have in the Hamiltonian the kinetic energy of the electrons, an external potential that is actually the atomic nuclei that form the field within which the electrons move. Then we have the interactions of the electrons itself, and finally, to get a total energy, we would actually also have to consider what are the nuclei themselves doing. That's actually not very relevant for what we are discussing here. So, as I said, we'll have to consider that all the electrons are interacting with each other. So we have an electron wave function that depends on the positions of all the electrons. So if you have n electrons, this is actually 3n coordinates. So this solving this is computationally expensive, and expensive is really expensive. I mean, the amount of work you need to do grows basically exponentially with the number of electrons in the system. It can be done for sort of for a couple of electrons, perhaps a handful, but anything approaching a real, even a real chemical compound, let alone a material that consists of hundreds of thousands and millions, I mean, huge numbers of atoms, is not accessible by solving this directly. So, important realization is we have actually the electron density. So that is basically the probability to find an electron, any electron, at somewhere in the system. And this is basically gets rid of what all the individual electrons are doing and just replaces it basically with the electron charge. And now this is just is a property that just depends on the one spatial coordinate. So as I said, solving this many-body Schrödinger equation can be very expensive. The cost grows exponentially. So in chemistry, physics, material science, there have been many methods developed to reduce the complexity by using some type of approximations on how to solve this equation. I name a few there, like a CI coupled cluster, or quantum Monte Carlo methods, but all of those are still very expensive and hard to deal with for real materials. What we are using is density functional theory, and that relies on the great observation by Walter Korn, and for which he got a Nobel Prize in chemistry, actually, and Hornberg, that you can actually find the energy of the system and quite a lot of other observables by actually solving everything in terms of the charge density of the electron density itself, and that this electron density minimizes this functional. So short aside, what is a functional? A functional is basically a function of a function. So an integral is a functional. So it takes a function and gives you a number. So we have here the kinetic energy, that's T, then the interaction of the electrons with the external potential, the Hartree energy, which is basically the electron-electron interaction, and then in red here, this exchange correlation functional. That is basically the carpet under which we brush everything we actually don't know about the how the electrons interact, what comes from the many bodies. So we know it exists, and for certain simple systems we have actually exact formulations for this exchange correlation functional, but in general we rely on a number of approximations. So what we know this exchange correlation functional exactly, we could solve the many-body Schrödinger equation exactly. But since we only have approximations, this is an approximate method. But you see, we have greatly reduced the complexity of our original problem from finding a function of 3n variables to a function of just 3 variables. But we still need to see how can we solve this. And to do this, you can realize that this actually gives rise to some sort of effective single electron problem. You see this equation here looks just like a Schrödinger equation, but it's called the Cohn-Sham equation. You solve it for these phi alphas, which are called the Cohn-Sham orbitals. They are not really exactly electrons as such, but they basically are a single particle representation of what goes on. And Cohn and Sham have shown that if you solve this equation, you can basically take these n lowest lying orbitals, and you'll get the exact same charge density as you would have gotten had you solved the many-body equation. So, and you see there, as you see there, enters this exchange correlation potential, which is related to this exchange correlation functional. So how do we solve this? So we start out with some initial guess for an effective potential, and from this get a new charge density, and that allows us to guess a new effective potential and iterate this until we've reached convergence. Now we're just left with solving a single electron equation. So how are we doing this? We're using a multiple scattering theory. So this is like what Hannah used, the Green's function method. So formally, a Green's function is basically the inverse of the Hamiltonian. In multiple scattering theory, you realize that you can write down the Green's function for a particle just propagating without encountering any nuclei. And the scattering potential that is represented by this nuclei. So you sort of say you have an electron starting at some site I, scattering through the material until it comes to site J, as you see down there. And then you can calculate this scattering path matrix tau that you see there that describes how the electron scatters throughout the system. And the main computational effort in this method actually is calculating this inverse. And once we know the Green's function, we, as you can see at the bottom, we can readily calculate the charge density. As you see there, by the fact that there's an imaginary, we are interested in the imaginary part, this all relies very much on a complex algebra. So there are various ways of how you can describe the system you're describing in the sort of, if you have a very small, simple periodic system, you could use the Coringa-Cohn-Rostocker method, KKR method. What you do there is you basically say, oh, the system repeats periodically. You basically do a lattice Fourier transformation of the system and can solve for all of these lattice points to find the solution. And this is a method, though, that scales cubically with the number of atoms in this repeated cell. So if we're interested in this ordered system, this would become too expensive if we wanted to describe a large disordered system. And as you saw, that's very important. I mean, even for simple materials like alloys, steel, bronze, brass. I briefly show two different methods for dealing with disorder and complex systems. The first one is actually something that Hannah already talked about, coherent potential approximation, CPA, which averages the probabilistic distribution of the atoms. And the other one is locally self-consistent multiple scattering method, which introduces an additional approximation to solve this Schrödinger equation in real space, and has a computational complexity that only grows linear with the number of atoms. So in CPA, as Hannah already showed you, you're basically averaging the Green's function in which you embed your single atom, so that this averaged Green's function behaves in the same way when you replace the different scatterers inside. So you're averaging, you're basically ensuring that you average get the correct behavior from an average scatterer, as if it if you have sort of an ideal disordered system. And this is a very effective method, because now, even though you only have to do calculation actually for a single atom. So if we want to go into more detail without having to do this CPA averaging, which, as you saw already in Hannah's talk, might have problems when the more local effects are important. We are using this LSMS method. But what we are doing there is basically we say that instead of allowing the electron scatter as far away as it wants, we are restricting the radius of how far an atom is allowed to scatter before it needs to, an electron is allowed to scatter before it needs to return from where it originated. And this now is, instead of scaling cubically with the number of atoms in the systems, only scales linearly. So we can deal with much, much larger supercells, so we can make an effective representation of what a disordered system would look like. And it also allows us to scale this method to the largest computers, like Summit, which we have available at Oak Ridge. So I can run a system with a handful of atoms on my laptop, but I can run a system with 250,000 atoms on Summit. And as I said, it scales really very nicely. And once we have this, we can get the probability of the materials. And now I think I'll be turning it over to Wang, who will show you examples on how to deal with the actual running calculations like this. And I'm open for questions. Any questions?
So I have just one small question. So as you showed that you are taking disorder potential as a starting point, right, for LSMS?
No, for the starting point for LSMS would be just the actual individual atoms. So you would create a representation of a disordered state. So you would place in a cell with hundreds of atoms or so randomly so if we're talking about the iron platinum nanoparticle that I had at the beginning, randomly iron and platinum atoms. So there's no effective medium in LSMS.
Okay. Okay. So and in the free particle Green's function H naught, that is the CuZn Hamiltonian, just where you are defining free particle Green's function G is equal to 1 by epsilon minus H naught.
So the H naught is basically the reference Green's function. So basically the electron propagator.
So
you can, there are actual ways of, instead of using free electrons, the free electron solution there, to use other reference systems, but that becomes too technical for this brief introduction.
Oh, thank you. Thank you.
I just had a quick question. You mentioned the last method you talked about, obviously being scalable because it's utilizing parallelization. Is that the only method that's making use of that, or are there other methods that are being developed more for parallel systems or anything like that?
So there are other methods that also are looking that are more along the wave function based. So I've been really talking mostly about multiple scattering based approaches. And you saw we basically formally invert the Hamiltonian. A large number of DFT methods actually diagonalize the Cohen-Sham equation, which is computationally has actually the same complexity. So they also would scale with n cube, but in principle there are some approaches that use spectral diagonalization based methods that also do some type of this real space decomposition to achieve better scalability. So yeah, I mean, LSMS is one approach, admittedly very well scalable, but there are other methods to achieve the scalability as well.
Any other question? Okay, there are no more questions for Markus. Next, Wang from Carnegie Mellon University, he will complete the presentation.
Okay, thank you. Thank you, Juana, for making this arrangement.
No problem.
Okay, to talk to everyone. I hope, by seeing your name, you know your username, okay? Your username will be served as your password when we do the practice. So this is a very simple practice we're gonna see. So let me explain what kind of work we can do with this. So today's talk is a kind of short tutorial of using MUST. This is the name of the project, also the name of the software package that Markus was talking about. KKR-CPA, the LSMS is all part of this this MUST package. So what is MUST? It's a stand for multiple scattering theory. And it's a method for solving the Cohen-Sham equation, which is a one-electron Schrödinger equation describing the electronic structure of solids. And specifically, this method calculates the Green's function of Cohen-Sham equation, which is a Schrödinger-like equation, and determining electron density by taking the imaginary part of the Green's function. That's being discussed by Hannah and Markus. And MUST is a computational tool for ab initio electron structure calculations. Okay, and so-called ab initio, it implies that electronic structure is determined based on the fundamental physical law, which in this case is quantum mechanics, rather than empirical models with adjustable parameters. So what we do here is a kind of recall Hannah's one of her slides showing these two routes towards the study of materials. One is a model approach, another is this ab initio approach. Okay, so this is a method try to quantitatively determine the real materials physics, the properties of the real materials. And of course there are other methods, ab initio methods. For example, like you may hear people were talking about like called VASP or Vin2K, ELK, ABINET, quantum espresso, and so on. There's many other methods as well. But all those other methods are based on solving the Schrödinger equation, differential equation, by solving the wave functions and calculate so-called band structures. But multiple scaling theory is different in the way that it calculates Green's function of the Schrödinger equation, okay, instead of solving the wave functions. So it's taking different approaches, but the whole goal is try to determine the density of states and the charge density of the electron. Okay, so the package is publicly available. You can find it by take this command git clone, and you can download this must package. And once you do that, a directory called must will be created on the local disk space. Okay, and so now we're going to show you how to run this must. We're going to take copper zinc as an example. Why copper zinc? Well, it's a brass. It turns out can be a random alloy. We are, this kind of material many people are familiar with. It's an ancient material, and then later on we really understand it is an alloy of copper and zinc. Okay, it's brass, different name called brass. So it's been long in history with us, with Asian civilization, and being used as doorknobs and sorts of utensil because of interesting physical properties and mechanical properties and other interesting like electrical and thermal conductivity and durability, all these different properties, so that can be used for different applications. So the interesting part of this material is that at zero temperature, copper zinc is an ordered structure. It's called a B2 structure. And so it looks like this. All right, so at low temperature, it's based at zero temperature, Kelvin, and copper and zinc arranged in regularly, that it's like a cube, right? At the corner is a copper and the center is a zinc. It's an ordered structure. But when you increase the temperature, there's a ordered disordered phase transition that each side is randomly occupied by either copper or zinc. Okay, it's become a disordered structure. So it's called a beta phase, and another name is called a A2 phase, A2 structure, or also called a BCC structure, body standard cubic structure. Okay, so it was a different name, but it all means the same thing here. All right, so this is the kind of property we're going to see. So on the one hand, copper zinc can be ordered at zero temperature, but also can be disordered, like this A2, this beta phase. Okay, so we're going to use different method to study the different structures. Okay, so you can get onto the site. You can look at the chat and see you have I have the link there. You click it in your browser. You can just log into your you can see this hub and then click it and then log in. Okay, so once you actually what's happened is on the must, and there's a tutorials, and there's a real tutorial called copper zinc. Then the code we're going to run is called a MST2. That's what it can. MST2, this single command can run either KKR, which is applied to the ordered structure, or KKR-CPA is designed to study random structures, or LSMS designed to study large unit cells because it's a scaling properties. So basically, it has takes three different type of input data. One data is a description data, another is position data, tells the structure of the material, and then the starting potential is defined for copper and zinc. And then to run it, all you have to do is just click MPI run, because this code itself being compiled with MPI for parallelization. And all this command MPI run space minus MP, then the next followed by the number of processors in the use. Then the command for running, which is under must_bin/ms2. That's where the executable is located, and then with the arrow and with the input data. All right, so that's how you run it. So there's a 3 tutorials and materials. One is called a B2 structure. It's an order structure. This is cop and zinc in the order. So we're going to use KKR method to do the calculation. The other is a random structure. Each side can be occupied either by copper or zinc. It's a disorder structure. Then we have to use KKR-CPA to do that. And to study the disorder structure, I created also a large unit cell, try to mimic the disorder structures, because the resource is limited because it's online, it's a cloud doing so. We only have a little small unit cell. It's only 16 atoms with 8 copper and 8 zinc placed on each side randomly. Okay, so it's a 16 atom supercell. We're going to use the LSMS method to do the calculation with the same command. Okay, so we're going to run this on something called a Jetstream. It's a Jupyter hub that it's kind of a computational. It's an on-demand computing environment that people can log on and use it. You don't have to worry about installing the code, and things have been set up for you. And you can run this example. We also have created a YouTube, thanks to Helen Kershaw. She did this and put a YouTube, and you can watch how this is example can be run on this Jetstream. So what you have to do is go to this web page, must-tutorial.com, and click Hub on the top banner. You'll see Hub. Click it and enter your username, whatever the username you find, you being assigned to you, and you use a username as a password. And then once you're into it, and you'll see on the upper right corner, there's something called a new. You click that, and you put this pull-down menu. There's one option is terminal. You click terminal. Then it will prompt with a new window for you. Okay, so you can enter the following command to copy this tutorial over. The must has been installed for you, and just all you have to do is copy that tutorial for you into your own home directory. Okay, then you can go to that tutorials CuZn/B2. This is where the example for running the B2 structure, which is all the CuZn structure for you. The tutorials, the input data is already set up for you. Then you run. Everybody just run out. Don't run more than 4 processes.
You are going a little. Hold on, you are going a little fast even for me. Could you go a little more slowly?
Okay,
Please?
slowly. All right. So first thing when you log in, you just copy that directory, tutorials, this /srv/tutorials to your own directory. Then go to, now you have a tutorials directory in your own home directory now. You go to that directory, you will see tutorials. There's a CuZn example there. Under CuZn, there's 3 different examples. One is B2, one is BCC. BCC is a disorder structure, and supercell, which is 16 atom supercell. All right, so there's 3 different structures for CuZn. Let's start with B2. To run it, all you have to do is just type this command. Actually, everyone has access to MS2 now. You don't have to write down all the paths, but this MS2 is already presented to you, so it can be recognized in your directory. So all you have to do is MPI run -n 4. You're going to use 4 CPU cores. Don't use more than that because we don't have that many available. Let's use 4, okay? Run it. It should take like 40-50 seconds to finish. It's very quick, okay? You can run the same way, okay, for other examples. Exact same command, okay? When you go to other directory, you do the same thing. Input data is already there, it's for you, okay? Now, I go to the next slide. Okay, here's a particular explanation. Now, on the B2 structure, if you want, I just want to give a kind of little explanation of the input, what input data is. It says that there are 2 atoms in the system, okay, because it's a cubic structure, and we're using KKR method method is 2 here. And for the position data, it shows the Bravais lattice, the structure of the system you're going to study. The first line is the lattice constant, the size of the unit cell. Then the following by these 3 lines is Bravais lattice. It's a cube. So there's 2 atoms in the system, copper and zinc, located at different locations in the cube. Okay. So the way, okay, here's the run it, and then so this is the position. Okay, you just run it, and then the input the code will take this position data and know where the atoms are, and then do the calculation for you. Okay. All right. So now we can do the same thing for KKR-CPA. The only difference is that now I'll have only 1 atom per unit cell, because every site is represented by so-called effective median, CPA median. That represents the average effect of the random alloy. So each site will be called a CPA atom. Represents that on average, what, either copper or zinc, on average, that site should be equivalent now. It becomes only 1 atom, even though in the fact that we have 2 atoms. Each side can be either copper with 0.5 concentration, and with zinc it's also 0.5. So there's only 1 atom here. That's why it's 1, and it's 1 atom is called CPA. Okay. Now this is the Bravais lattice is different, because I don't want to spend too much time to explain this, but if you learn the solid state physics, you know what that really means. It's a kind of primitive unit cell now. So on each side, there's a 50% of copper, 50% zinc. So with this is the input, you can run with the same kind of command. You run these calculations. Okay. So I give an example of the output. The simple output is in the K file. That it tells that this calculation runs 17 iterations. It finishes. Okay. So the total energy is given by this. This number plus this number will give you the total energy. Okay. So that's the total energy of the atom for this random alloy. For other examples, you have the same thing. You have this K file and look at the last line of that. It tells you what total energy. And then actually, what you can do is you can change the lattice parameter. You can make a plot. What is lattice parameter? Lattice constant. Also no, because remember we have a cube. For the random alloy, each side can be either copper or zinc. I have in my position data defined the lattice constant, the value. Okay, it can vary that number, and do the calculation. You get total energy for that particular lattice parameter. Then you run a set of calculations for different lattice constant values. Then you can make a plot. What you see is it becomes this parabolic curve. Okay, each of the dots represents a particular lattice constant I use for the calculation, and you find that there's one particular lattice constant has the lowest energy. Okay, so what do we learn from the total energy calculation for this random alloy? This is the output from the KKR-CPA. Is it tells you what's the equivalent crystal structure. That you can run different crystal structures, you get total energy, right? So this is one crystal structure that has the lowest energy. So that's called equilibrium crystal structure. In this case, actually, the turn out BCC has the lowest total energy, and it also tells you the lattice constant. What's the equivalent lattice constant? In this case, it's 5.53. Okay. Remember, I know it's I emphasize that it's t equals 0 because all the calculation we assume temperature is 0. We don't have temperature here. Okay. Now, so this tells you it's the equivalent lattice constant. Okay, and also tells you some mechanical property of the alloy. You see, when you stretch the crystal or compress the crystal, the energy quickly increases. All right. Depending on how quickly the increase or slowly increase, it tells you how soft or how hard or how soft the material is. So if the energy increases quickly, means the material is very hard. Or increase slowly, that means the material is very soft. Okay, some kind of mechanical property will be also telling. So it's kind of very useful from the total energy calculation. It tells you a lot of things. Okay, so another example for running supercell calculation, we're going to use LSMS. This time before you run it, you have to be careful. For the input data, now we have 16 atoms in the system. All right. So we're going to use the method 1, which is the LSMS, and this is configuration data. But now you see that this is I'm just going to use this as lattice constant. This is my cube, my box. It's a 2 by 2 by 2, but multiplied by the number. It's the actual size of the unit cell box. So this is 16 atom copper and 8 copper and 8 zinc in it. Actually, it's put in randomly. All right. So there's 16 atoms here. This tells you what's the local interacting zone. Markus didn't have time to explain that. It tells you for the real space calculation, it needs to tell there's a cluster size. That's kind of way of for making approximation for the calculating this kind of Green's function. The larger this size, more computational costs it will be. Of course, when the size is infinite, that's the exact solution. Okay, but now we'll make an approximation. So in the example, it's a 12.1, but actually it's still too big for running on 4 processes. So I hope you change the number to 8.0 because we're going to use 4 processes. If you later on want to come back, try 12.1, you might want to run it on 16 processes. So it runs pretty fast. But to get it done in a shorter period of time, change it to 8.0 and run it. All right, and just run this command. Okay, do this calculation. All right. So finally, what we're going to get for 3 different structures, we calculate total energy for each of structures. They have the same size. Okay, the lattice constant is the same. Okay, we have 3 different total energies. Which one has the lowest total energy? It tells you that at temperature equal to 0, what's the most stable structure? Okay, so by comparing this total energy value, so obviously this one has the lowest energy. Remember, this is a negative. Okay, so this one has the lowest total energy. So this B2 structure is indeed the most stable structure at T equal to 0. Okay, that's what we expect. But that's what's experimentally found, that B2 is the ordered phase, which has is where the temperature equals 0, how the alloy exists, and this complete disordered structure has the highest energy, and slightly higher than this. This supercell, it's a kind of disordered, but it's not. It's still it's a little bit. 16 atom is it cannot be really represent totally totally random, right? But more or less mimic the disordered structure. So it has the higher energy than the completely ordered structure, but still lower than complete disordered structure. So that's what we expect. So this is from total energy calculation, you can really get a lot of physics out of it. Okay. So also you can compare what really agree with what experiment telling you. Okay. So that's all the tutorial for this running must. And everyone, if you are interested in continue and try to more different other calculations, you can download must yourself on your own laptop. It runs on your laptop as well, and give it a try. And it can be applied to many other ambient electronic structure calculations. Okay. Now that's all I want to say. Any questions?
Yeah, and I have a question. The difference in energy between the zero temperature configuration and, for example, the completely disordered is comparable to the transition temperature?
Okay, that's interesting. Yes, you can see the energy difference. You might want the energy difference to estimate transition temperature. But it turns out it tends to be overestimate all the disordered transition temperature. I think Markus has more to say about it because you might want to introduce a more sophisticated method to estimate what's the because there's entropy involved, right? So yeah, I think there's a more sophisticated method to do that.
Yeah,
so energy itself is not sufficient. Yeah.
So what you can do, for example, is there are actually 2 approaches. One is using CPA and look actually at concentration fluctuations. So you do CPA with basically with the cesium chloride structure and look at the fluctuation of the concentration between those, and look at can calculate the instability against the formation of concentration fluctuation waves. And that's something that for example, Julie Staunton did about 20-25 years ago. Or using LSMS, you actually can use LSMS within a classical Monte Carlo approach and have Monte Carlo moves changing the site occupations, and that also would allow you to then give you quite good within basically within about 100 Kelvin the correct transition temperature. That's something that I did with a postdoc of mine a few years ago. If you just do this, though, you'll have to be aware that these types of calculation then still neglect the phonon contribution to the entropy, which would account for the remaining about 100 Kelvin or so in the transition temperature.
Yeah, I guess a very naive way of do that, if I look at the energy difference, and then you let that equal to KBT, right?
Yes, yes.
KBT. That's the easiest way to do it.
I don't expect to be exactly the same.
Yeah. But then you don't have like an entropy term. There's no entropy term. Yeah.
I mean, there you're basically just looking at the enthalpy, so there's no entropy.
Yeah. That's right. So the that website for the must practice, the website can do come back and try anytime you want. Try more processes. I think can use up to like 40 processes, I believe. So you can try on your own, and that's later on. Doesn't have to be right now, and you can try that later. Any other questions?
Yeah, I have another question. How are you releasing your code? I mean, with what,
release the code being, let's see, you can download it. It's being, we'll keep updating it, and it just, let me see. I have a slide that shows the.
I mean, anybody can use it.
Oh, yeah, anybody can use it.
It's open source. It's open source. It's a BSD3 license.
Okay.
Yeah. It's just like other public code, like EBINIT, quantum espresso, and we have must.
Okay, but other people can start with this code and make modifications and license, no?
I think so, right? Markus, do you know, are you familiar with the license? I have no problem with people modifying it.
So the license is a BSD3 license, so this is fairly permissive, so anyone can basically download it, do whatever they want to do with it, as long as they give us credit, but don't hold us liable.
Okay.
But of course, if someone does it, I mean, we really would greatly appreciate if someone develops some new capability or so, if they would contact us to see if we want to incorporate it. But in principle, given that the license term, you can do with it whatever you want.
Okay.
Okay, there's another question. Let's see.
Yes, yeah, it's about if the software will be available for the party.
For how long? We created 40 students account,